start with a new topic, compressible flows. This topic discusses about a title which in a sense is misnomer. Why? Because when we say compressible flows, we essentially talk about a particular class of flows, whereas almost all flows will have some sort of compressibility or the other. So, what is so special about this type of flow which we call as compressible flow? So, compressibility in a common sense perspective has something to do with change in density. This is not a formal way of defining what is compressibility or incompressibility, but effects under which a fluid flow becomes highly compressible. One of the hallmarks is a strong change in density. However, that is not a technical definition. The reason is that by definition we classify a flow as incompressible when there is no change in volume of a fluid element. This is a pure kinematic way of defining the flow, defining the incompressible flow. So, incompressible flow essentially boils down to the kinematic definition that there is no change in volume of a fluid element, which in terms of the velocity vector can be written as divergence of the velocity is equal to 0. For a one dimensional incompressible flow, you have this boiling down to where u is the velocity component along x. Now, let us consider a general one dimensional steady flow. When we say general, we essentially mean that we can accommodate the effect of compressibility in the analysis. So, when we do that, first of all, because it is steady flow, there is no density variation with respect to time. So, this is the corresponding continuity equation for one dimensional steady flow. Remember that this is not a pure kinematic constraint, this follows from the conservation of mass, whereas this is a pure kinematic constraint. So, from the conservation of mass or the continuity equation, when all other terms are dropped for one dimensional steady state steady flow, you get this. So, you have recall that for one dimensional incompressible flow, this term is 0, and because this term is 0, this the other term also has to be 0 for one dimensional incompressible flow. So, if it is not incompressible flow, the first change is that this is not 0 and therefore this is also not 0. So, deviation of this from 0 hallmarks the deviation from incompressibility in a one dimensional framework. So, if this is not 0, question is how much is this? How much is this? We can say that whatever is this, it must be of the same order as this term. So, the order of this is rho delta u over delta x, the order of this is over u delta rho over delta x. So, we can say that for the sum total of these to be 0, this order and this order must be equal, algebraic sign wise they are opposite, so that they cancel each other. So, rho delta u is of the order of u delta rho. Okay. So, you have delta rho is of the order of rho delta u by u. As we say intuitively, this delta rho indicates a degree of compressibility. Right. Now, we can say that from the one dimensional equation for momentum conservation, which is essentially the Euler equation for inviscid flow, we can write so recall that one dimension Euler equation essentially describes the equation of motion for inviscid flow, and for an inviscid flow you can write the equation of motion in this way. Okay. So, this we have derived in one of our lectures under dynamics of inviscid flows. We have to keep in mind that for a general flow this is v dv, where v is the resultant velocity vector. For a one dimensional flow it is just u du. So, the general 3 dimensional scenario is cast into the one dimensional form, and we are neglecting the gravity effects here. So, you can write delta p, so this is of the order of delta p by rho, and this is of the order of u delta u. Again we can say that because these two terms are of the same order, delta p is of the order of rho u delta u. So, now you can write delta p by delta rho is of the order of, just divide these two, is of the order of u square, right. So, the velocity of flow is related to the rate of change of pressure with respect to density, and when these two are of the same order, we can say that compressibility effect is important. So, when is compressibility effect not important? When they are clearly such that the order of this is much less than the order of this. Okay. So, what this physical quantity is in terms of compressibility effect propagation through a medium, that needs to be carefully studied. So, to understand that, we consider a simple experiment like this. So, we have a piston in a cylinder and this piston is pushed towards the right. When this piston is pushed towards the right, so let me hatch it to indicate that it is a piston, there will clearly be some molecules which are adhering to the piston which will feel the effect of this compressibility. This is what you understand from your physical sense what is compressibility. But far away from this, the molecules which are sitting, they may not instantaneously feel the effect of compressibility. So, the effect of compressibility eventually how it is transmitted from one end to the other. So, there is a compression rarefaction in this way. So, first molecules are compressed and then the effect of compression is transmitted to the next layer of molecules and then there is a rarefaction of the previous layer of molecules. In this way there is an alternate compression rarefaction in this manner. In other words, we can say that because this is alternate compression rarefaction like that, something like a sound wave propagates. So, this in general terms is called as the disturbance of a pressure disturbance propagation in the form of a pressure wave. So, this wave front which is drawn by this yellow line moves towards the right with a velocity c. So, when it moves towards the right with a velocity c, so here there is a discontinuity, not a finite discontinuity but an infinitesimal discontinuity. So, there is, so we have to think about certain aspect very carefully. When we have a discontinuity, we can have a finite discontinuity which we will later on learn as a shock wave, and there can be an infinitesimal discontinuity for this weak waveform to propagate. So, here if you have a pressure P plus dP, here you have a pressure P, here if you have a density rho plus d rho, because of the significant compaction, here the density is still rho, here the velocity is du and here the velocity is 0. So, this, so if you want to ask that how will I know where this front is located, the simple answer is it is located at the starting of a location where the fluid is undisturbed. That means the fluid has not yet felt this compaction effect, that is where this is located. So, this is like a whistle blower which is blowing a whistle that see I am being compressed, so you also should be compressed. So, that message it is propagating from the left to the right by virtue of the travelling of a wave. So, the question is that when you have this change in pressure and you have a change in density, how those are related to the speed of propagation of this disturbance, which is also called as sonic speed. To understand that, let us assume that there is a this front, this line is shown here. Let us assume that it has an area of A, pressure on this side is P plus dP, density on this side is rho plus d rho. Because this is a moving front, to make it stationary we superimpose a velocity c in the negative or from the right to the left. So, this front is moving towards the right with a velocity c, a velocity of c is superimposed on it so that it appears to be stationary. So, if a velocity of c is superimposed on it, it should be superimposed on both sides. So, if c is superimposed here, so here it will be c minus du in this direction. Pressure wise this is P, density wise this is rho, velocity wise this is c, this is c minus du, du is along the other direction. Next what we will do is we will consider a control volume. We will consider a control volume centered around this and write mass balance and momentum balance. So, mass balance, so what is the mass flow rate from with respect to the stationary thing from right to the left? So, mass balance. On this side what is the mass flow rate? The density is rho plus d rho and the velocity is c minus du. Momentum balance. Resultant force along the left direction, what is that? So, P into A minus P plus dP into A is equal to m dot times V2 minus V1. So, V2 is C minus du minus C. Now, we can simplify these equations. First of all, let us simplify these terms. So, rho into C minus rho du plus d rho into C minus d rho into du. out of these 4 terms, this term is of lower order as compared to the other terms, and so this can be neglected. Then if you compare the terms in both the sides, this rho into C gets cancelled. So from here you get rho du is equal to d rho into C. The second equation, the momentum balance, so minus dP into A, in place of m dot you can write rho AU into minus du. Okay. So you can write dP is equal to rho u du. Right. Sorry, m dot is rho AC, not rho AU, right, rho AC, yes. So this becomes rho C du. So m dot is rho AC, right, rho AC. So now if you divide these two, this one and this one, why our objective is to get a measure of this delta P by delta rho. So dP d rho is equal to rho C du by rho du by C. So this is C square. So we can say that order of magnitude of this is C square. That means what we are essentially comparing to understand the effect of compressibility is the comparison between U square and C square. So we define a quantity called as Mach number, so what is our important benchmark for onset of compressibility is m square is of the order of 1, not m of the order of 1, m square of the order of 1. So when compressibility is not important, that is not important when m square is much less than 1. That is the wave motion does not induce a significant velocity by virtue of compression and rarefaction of the medium. So when this happens, so much less than 1 means we can say maybe m square of the order of 0.1 when we say compressibility is not important. So, this means that m is of the order of 0.3, around 0.3, not of the order, around 0.3, because 0.3 square is 0.09, which can be roughly told as 0.1. So, this brings us to the rough thumb rule that if the Mach number is 0.3 or less, we neglect the compressibility effects. So, given a particular type of flow, we first try to analyze what is the Mach number. If we say, if we find out that the Mach number is much or the Mach number is 0.3 or less, then that gives a clear indication that compressibility effects need not be considered. So, although that type of flow is a compressible flow in a strict sense, the compressibility of the flow can be neglected. However, as the Mach number increases from this to higher and higher values, say 0.4, 0.5, 1 and greater than 1, we say that the compressibility effects are more and more important. So, this C, which is called as sonic speed, based on this C, we say that Mach number less than 1 is subsonic flow. Mach number equal to 1 is sonic flow, and Mach number greater than 1 is supersonic flow. So, the question is that obviously the compressibility effect is more and more important as the flow from subsonic goes to supersonic, that means as the Mach number increases. Now, given a particular physical situation, one has to understand that the Mach number is not a constant for an entire device always. For example, if there is a change in cross section of a device, the Mach number changes. So, there is a possibility that the Mach number has a transition as we go along a device. So, what type of device? Maybe a nozzle. So, when you have such a change in Mach number, it is possible that the flow which was earlier supersonic may become subsonic. So, it is possible to have a change in Mach number. So, we cannot designate a flow by a unique Mach number if the Mach number is a variable. So, how the Mach number varies and what are the parameters on which the Mach number depends, that we will look into in the next lecture. Thank you very much.